Hi there, my name is Philip D and I work in the Faculty of Health's Academic Development Department, or the ADD, which was previously known as the PDD, the Personal Development Department. And this is the fourth instalment in a series of 5 videos covering key concepts of quantitative systematic reviews. So far in this video series, we have covered in video 1 in broad terms what a systematic review is, why we should carry one out, and the main components that make up a systematic review as a piece of research, thinking in particular about you doing this as the final component to your MSc project. In video 2, we took a deep dive into an actual published systematic review. This allowed you to see what a write-up of a systematic review might look like, although as we were looking at a published paper, that particular example was much shorter in length to what you yourself will produce. In video 3, we looked in some detail at the key statistics that you will come across in your reading of the primary research papers. I introduced you to the concepts of the hazard ratio, the odds ratio, and the risk ratio. Now in this video, video 4, I also intend to explain in context other key statistics that are particularly specific to doing a meta-analysis within a quantitative systematic review. And finally, in the very last video, video 5, I will show you how to actually carry out a meta-analysis using the freely available program RevMan. So, on with the video, understanding the statistics of a meta-analysis. Now, according to Harrison Taylor from 2014, a meta-analysis is a technique for bringing together results from a number of similar studies to give one overall estimate of effect. But before we have the confidence to do this, we need to dig deeper into first some familiar concepts and then to introduce some newer ones. So here's our plan for this video. The intended topics to cover are all related in one way or another with the structure of the subsequent forest plot that is produced. We need to extend our understanding of the mean and standard deviation to introduce the standardized mean and then something called the standardized mean difference. We will have a first look at how data is combined, otherwise known as pooling, in order to create a single summary mean and associated 95% confidence interval that represents all of included studies. I will only be making mention of this early on, but we'll develop our understanding a little near the end of the video. We then need to be able to appraise whether we feel our primary data is too spread out beyond that expected by chance alone. And this leads us to cover in more detail than we have considered so far the idea of heterogeneity and how we can measure it and evaluate it. Related to this is the idea of sensitivity analysis, where we see how each paper in our included studies is contributing to the heterogeneity. If the nature of our extracted data demands, we might also need to carry out a subgroup analysis. This generally occurs if the data we are extracting is coming from different groupings of participant characteristics. And finally, we also need to think about an important decision, taken in the light of all of our evaluations so far, as to whether we choose the fixed effect model or the random effects model. So let's just remind ourselves what a forest plot looks like so as to see where all of these concepts are located. We saw an example of such a plot in video 1 and went into a bit more depth when we looked at a specific paper in video 2. We need to look now with a different focus at all aspects of what this summary plot is telling us. Now this is the forest plot taken from Derm et al. 2021, which was looking at non-steroidal anti-inflammatory drugs for acute gout. Amongst other measures, they compared 2 drugs, NSAIDs, NSAIDs, versus COXIBS, COXIBS. Now there's a lot of information contained in such a plot, so let's take it slowly. So a forest plot, as we know, is simply a combined, tabulated and visual summary of the results of the meta-analysis. And this is often the endpoint of a quantitative systematic review. There are several columns of information in the tabulated section, much of it numerical, a plot of dots or squares and confidence intervals, and at the bottom left some further information regarding what is called a test of heterogeneity, which may also be part of a sensitivity analysis and possibly a subgroup analysis. In this example, in column 1, we can see that 6 papers were considered. For each paper, they gave the mean difference, MD, and the standard error, SE, both of which I need to say more about on the next slide. Next, we have the weight, which I'll also unpack in a while, and then, for each paper, a repeat statement of the mean difference, but also now with the lower and upper range comprising their 95% confidence interval, which you will remember from the last video is a sort of measure of precision. Then we have the first part of the actual forest plot, which is a visualization, again for each paper, of their overall results. The red squares represent the mean difference, which are also called the point estimate of the mean difference, and these are given for each paper. Note here that the 95% confidence intervals are represented by the horizontal lines. Notice only one of these sets of confidence intervals avoids crossing the zero, the null hypothesis line. This means that only one of the primary studies, Rubin 2004, was itself statistically significant in its own right. The rest were not. You will have also noticed that squares are all slightly different in size. This is because the forest plot gives bigger squares for results that carry a greater weight, i.e. a greater level of importance. This usually means that those primary studies that had a larger sample size are given more of a say in the final calculation, i.e. in the final combination pooling. On some systematic review forest plots, you might see circles instead of squares, but again their size will have the same interpretation as here. You can also see a vertical line passing through or close to all of these plots, and this line represents the measure of no difference, i.e. the null hypothesis, and as we are talking about mean differences, this particular line therefore passes through zero on the horizontal axis. Had we been talking about a ratio such as odds ratio, risk ratio or hazard ratio, that line would pass through the value 1 on the horizontal axis. Now it is this part of the plot that you will need to dwell on. Are the points distributed broadly across the same line, or is there quite a bit of variation? In this case, I'd say there's quite a bit of variation, as 2 point estimates lie to the left of the zero line, 2 lie to the right, and 2 are pretty much on the zero line. We next think about the black diamond. This is when all data across the 6 papers were combined, i.e. pooled. The overall average is the line you can imagine running vertically to the top and bottom corners, the vertices of the diamond. So here the overall pooled mean is just to the right of the zero line at 0.08. The horizontal width of the diamond represents the 95% confidence interval for the combined or pooled data. Here to the left, we also are given the actual values of 0.08 for the overall mean difference, with a 95% confidence interval of minus 0.07 to 0.22. Notice how this overall result has a confidence interval which includes 0 as a plausible value. Therefore, there is insufficient evidence to reject the null hypothesis of no difference between the 2 pain relief drugs. In other words, the actual small difference as measured across all studies is not statistically significant. So here we see an example where one of the contributing papers did have statistical significance, and yet when combined with all other similar papers, that statistical significance was lost. And the last part on this forest plot at the bottom left, I've recorded the results of the tests for heterogeneity, and finally, on this occasion, there was no subgroup analysis carried out. The measured value for heterogeneity is given as 53%, and we'll discuss what this means a little later. One small point. Sometimes you will see arrows on one side or the other of the confidence intervals to indicate an incomplete view, i.e. because it has gone off the scale displayed on the bottom axis. This is done simply to allow a clearer zooming in on the main findings. The complete data is of course given in numerical form in the left-hand table. This is apparent in this plot taken from Kuipers et al. 2013, looking at the long-term effects of cognitive behavior therapy, CBT, compared with pharmacotherapy, PHA, in the treatment of adult depression. You can see that only one primary study, that from Jarrett 2000, favours PHA. The others favour CBT. As these are measuring odds ratio, the line of the null hypothesis on the horizontal axis at the bottom is 1. Therefore, you can see that only one primary study, that from Jarrett 2000, favours PHA, i.e. is to the left of 1, and all the others favour CBT to the right of 1. I want to take a step back and say a tiny bit more about the mean. Let's go back to our nice, small, easy to play with dataset that I used in the last video. You may recall the mean, which is sometimes denoted as x bar, was 3, which was the total, 21, divided by the number of values in the dataset, which was 7. Okay, I can use a calculator to find the standard deviation, and this comes out to be 3.605, and this is a measure of the spread of values in our dataset. The smaller this value, the more tightly bunched together are the values in the dataset. Okay, so far so good. We can imagine this sample to have been drawn from a much larger population, so we must realise that the mean we have just calculated can only be the estimate of the population mean. The same is true for the spread. This standard deviation is known as the sample standard deviation and is therefore an estimate of the population standard deviation. Another term you will come across in the stats literature is to say such values of mean and standard deviation are what is called point estimates, i.e. a point estimate is just a fancy way of saying our mean and standard deviation are themselves estimates of the actual population parameters we are trying to get at. The same is true when you see measures of hazard ratio, odds ratios and the like. If they have been calculated from a finite sample, i.e. a subset of the population of interest, which they nearly always are, then they and their corresponding standard deviations are point estimates. Okay, next thing to mention is the 95% confidence interval. It is not the same thing as a standard deviation, but, at least for the case of the mean, is calculated from it and the sample size. To calculate the confidence interval, we first need to find the standard error in the mean, or SEM, and this is calculated by dividing the sample standard deviation by the square root of the sample size. In our case here, the standard error is 1.363. Whilst the standard deviation is fairly constant for different samples taken from the same population, the SEM becomes smaller as the sample size increases. This is because the sample size appears in the denominator in the calculation of the SEM, and as we might remember from school, as the denominator of a fraction increases, and assuming the numerator stays the same, then the value of the overall fraction becomes smaller and smaller. Then, in a somewhat simplistic version of what comes next, you double this value. For us, that is 2 lots of 1.363, which is 2.726. This is your range amount for the 95% confidence interval. So you add this value to your sample mean to get the upper confidence interval value, which here becomes 5.726, and to find the lower confidence interval value, you subtract this doubled SEM from your sample mean, which here becomes 0.274. So we can now express the overall result as the mean equals 3 with a 95% confidence interval of 0.27 to 5.73, rounding to just 2 decimal places for convenience. If we are comparing drugs, therapies or some procedure via data across, say, 2 groups, then it is common to see the difference reported. The sign of the difference will indicate which direction the difference is pointing to. If different units, i.e. scales, are used to measure the same outcome, then we use the standardized mean difference, SMD, instead, along with their corresponding 95% confidence intervals. SMDs are derived by simply dividing the mean difference by the standard deviation, resulting in a measure of treatment which is then unitless, i.e. a pure number. If the mean difference of a measure is, say, 3, and the corresponding standard deviation is 5, then the standardized mean difference is 3 over 5, which is 0.6. So the standardized mean difference is a way of expressing the difference measured as the number of standard deviations that this difference or shift represents. This is also known as Cohen's d, and according to Cohen 1988, a standardized mean difference of up to 0.2 is considered to indicate a small effect size. 0.3 to 0.7 is considered a medium effect size, and 0.8 and above is a large effect size. There are different versions of these boundaries suggested by different authors, so do make sure you consult a recent textbook on this to guide you. For example, sometimes, though certainly not always, effect sizes expressed as SMDs are considered to indicate a clinically relevant effect if they are larger than 0.5. Now, just as the mean difference is divided by the standard deviation to obtain the standardized mean difference, a similar division occurs for the 95% confidence intervals. For this process, the standard deviation of the pooled control group is normally used. According to Derm et al. From 2012, page 12, some papers, upon completion of the analysis, translate the final pooled standardized mean difference back into a mean difference using the control group standard deviation at baseline to represent the population standard deviation on a common scale, which can then be more useful to clinicians who will, after all, be the ones evaluating the research. Of course, this is just one way that data is represented. We also have dichotomous data for which odds ratios, risk ratios and hazard ratios are used, and in such case there is never any need to standardize, as these measures are already in a standard form, so to speak, as they are a ratio. The test statistic referring to the heterogeneity across the 6 studies recorded as a tau square value here of 0.02, a chi-squared value of 10.68, and the more recognizable measure I-square, which here is 53%. The key test statistic from this range to consider for the beginner is the I-squared value. Now, this is a value that lies between 0 and 100%, and the lower this value is, the less heterogeneity there is, which is what we want. So for the Derm et al. Paper shown here from 2021, their value of I-squared was 53%. But how do we interpret this? Now, the Cochrane collaboration has suggested these guidelines for interpreting the value of I-squared. And I think just by looking at the values, you can see one problem I have with this. These overlapping boundaries are less than helpful from my perspective, although it does reflect possibly the lack of consensus regarding this. Nevertheless, the value of 53% from the Derm et al. Paper might plausibly be interpreted as moderate heterogeneity. Back in video 2, when I looked at the anatomy of a systematic review paper, I referred, in passing, to both homogeneity and heterogeneity. The concept of homogeneity often appears in primary studies, as it is concerned with how similar or how uniform, say, the variance is across 2 or more datasets, i.e. where we are looking at the comparative spread in data across 2 or more groups. The prefix homo means same or similar. This is important in primary research because it informs the author which statistical test they should be using. For example, if the spread is too different across 2 or more groups, then they cannot regard their data as being parametric, and so must then use a non-parametric test such as the Mann-Whitney test, rather than a more powerful parametric test such as a t-test or an ANOVA test. This idea of parametric versus non-parametric data is further explored in my video on inferential statistics, which I will put as a link at the end of this video. On the other hand, tests of heterogeneity is the flip side of this and looks at evaluating the degree of difference or non-uniformity in the means and spreads across two or more databases, i.e. across two or more papers. It is therefore of direct importance to a systematic review where we are now looking at a selection of primary studies side by side, so to speak. If the means or other forms of measure such as odds ratio and hazard ratio are too different across the primary studies under review, then this poses a potential threat to the validity of the ongoing systematic review and so is typically considered as part of a meta-analysis. We start firstly by looking at the heterogeneity of effect sizes. So where there is variation across studies, we call this an amount of heterogeneity. The study of heterogeneity acknowledges that this variability can manifest itself in three ways. We have clinical heterogeneity, which arises from the variability in interventions, participant characteristics and outcomes. We could also have methodological heterogeneity, which arises from the variability in the quality and design of the trials. And finally, we have statistical heterogeneity, which arises from the variability between the results of the papers under consideration, i.e. is this variability more than would be expected due to chance alone? Now I suggest you look at Borland 2017 on page 248 for a further discussion on this. But after that, I would recommend you consult the online version of the Cochrane Handbook of Systematic Reviews and see section 10.10, for which I provide a direct link in the reference. For a more mathematical take, you might also consult chapter 16 in Bowenstein, who covers it in way more detail than you probably need. Finally, note in some textbooks, they only talk about two sources of heterogeneity, clinical and statistical, where in those cases what we are calling methodological heterogeneity is considered part of the clinical heterogeneity considerations. So starting with clinical heterogeneity, to quote Gagnier et al. 2012, this arises from differences in participant characteristics, e.g. sex, age, baseline disease, severity, ethnicity, comorbidities, etc. Or types or timing of outcome measurements and intervention characteristics, e.g. dose and frequency of dose. This source of heterogeneity can cause significant statistical heterogeneity and therefore inaccurate summary effects and associated conclusions, thus misleading potential decision makers and others. Methodological heterogeneity is where there is variability in the trial design. This could be aspects of the variations in the study design, such as defining and measuring outcomes, duration of follow-up, and other methodological factors. Again, quoting Gagnier 2012, they give the example of trials that do not adequately conceal allocation to treatment groups may result in overestimates in the meta-analytic treatment effects. And finally, statistical heterogeneity is generally simply referred to as just heterogeneity, and it is where there is a variability in intervention effects observed in different studies. These may simply be due to the play of chance alone, or indeed may arise due to clinical heterogeneity and or methodological heterogeneity. In other words, it is the calculated amount of heterogeneity across all of your studies that then might be explored further. So whatever the source of the heterogeneity, it can lead to misleading summary effects and therefore any conclusions drawn. Now you'll see two models mentioned in a forest plot and mentioned in Revman calculations that you yourself may be carrying out. And therefore you will need to make a choice between these two approaches to pooling the effect size. And these models are called the fixed effect model and the random effects model. We need to explain or at least introduce the difference between these two approaches, as you will come across them in papers and of course in your own analysis. First up, and generally the most preferred, but only if it's permitted that is the fixed effect model. If there is confidence on your part that all of the studies in the review are showing similar estimates i.e. if there is no significant heterogeneity across the studies, then we might be pretty sure that all measures are from the same population. That means that there is a general uniformity of the underlying population parameter being measured, in which case we then set our software, e.g. RefMan, to fixed effect mode, and so calculate a common estimate from all of the data. To help us establish that this is indeed the case, we always start by first eyeballing the forest plot, as well as looking at the various measures of heterogeneity, and consider all the details from the data extraction table. In this approach, the pooling, i.e. the combination of all the data, will take a weighted approach whereby the weighting, i.e. the amount of importance or consideration given to each study, is, according to Bruce et al. 2008, page 414, related to the inverse of the variability. Understandably, more emphasis is given to those studies with the larger sample size, or equivalently, as a larger sample size will lead to a higher precision and narrower confidence interval, this will indicate a greater level of information carried by such studies. If, on the other hand, we do not feel there is a general uniformity of the underlying population parameter being measured, i.e. if we deem the heterogeneity to be unacceptably large, then we set our software, RefMan, etc. to random effects. And what this means, according to Bruce et al., again page 414, is that we suspect there is a different underlying effect for each study included in the meta-analysis. In other words, the effects for the individual studies are assumed to vary about some overall average effect. According to the Cochrane Handbook, Chapter 10, random effects meta-analyses allow for heterogeneity by assuming that underlying effects follow a normal distribution. It is used, therefore, to control for a larger degree of heterogeneity, but such a meta-analysis must be interpreted with caution. Okay, so we can't put this off any further. We finally need to talk a little bit about how researchers pool, i.e. combine their data as part of the meta-analysis process. Now, we won't go into great depth, and I'm sure you'll thank me for that, but it's important that we at least appreciate some of the concepts behind pooling data. As an example, let's look at the mean, which is one of the more common measures of average. Now, remember in the last video when we talked in detail about the average, and we had this data set, which we have already made use of. Well, you remember that the mean of this data set still is 3. So let's re-express this result as x bar, which is posh stat speak for the mean, and remind ourselves that the sample size was 7. Now let's introduce another mean from another data set, and let's suppose the mean from this new data set is 5 and the associated sample size was 20. Now let's try to combine these means into an overall average. What value do you think this overall mean will take? And I'll invite you to pause the video for a moment and think about it. Well, if you thought that the overall mean is probably 4, because after all, that is the mean of the two values 3 and 5, well then you would be wrong. The actual pooled mean, x bar, is 4.48. Much closer to that value of 5 than it is to that value of 3. And this is because the mean of 5 came from a much larger data sample. It had 20 items in it, remember, compared to the mean of 3, which came from a data set of only 7 values. So we need to give a greater weighting, a greater level of importance, if you like, to the mean value of 5 because of this larger relative sample size. So here's how I work this out. It's fairly straightforward if you think about it, I hope. Now, we already know that to find the mean of any set of data values, we need to know the total of those data values. Then we divide this total by the sample size. Well, for group 1, we don't need to have access to the full original data set. We do know the sample size, it's 7, and to get the total for this group 1, we just multiply the mean for group 1, i.e. 3, by the sample size. So 3 times 7 is 21, which you will recall is the total for that original data set. Next, for group 2. The total for group 2 will just be its mean, 5, multiplied by its sample size, 20. Well, 5 times 20 equals 100. So now we can see that the overall total across both groups is just 21 plus 100, which is 121. And then we must divide this total, 121, by the overall sample size, which is just 7 plus 20, 27. And so, with a calculator, I worked out 121, divide by 27 to give 4.48148, blah, 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 which I then just rounded to 4.48. Now, I will leave it there, as the mathematics is much more involved for working out the standard deviation, and from that, the confidence interval, for pooled data, but suffice it to say it also involves taking into account each standard deviation and applying a weighting according to the sample size. So, in summary, in this video we have extended our understanding of the mean to include the standardized mean difference. We have looked in great detail at most of the output that is given in a tabulation and a forest plot as part of a meta-analysis. And this led to a discussion of heterogeneity, its origins, and the main test statistic used being the value of I². It also led to a short discussion of the fixed effects model versus the random effects model, and we finished with a look at how data across multiple research papers is pooled using the example of pooling the means. Now, of course, there is a lot more to the underlying statistics than we have touched upon in this video. Again, we must acknowledge that every systematic review is different, and therefore, for your own systematic review research, there may very well be further areas that you need to read up on. The Cochrane Handbook of Systematic Reviews is always an excellent place to consult, along with Boland et al. And others from my reading list. And I would always expect you to search in places such as even YouTube to see examples that stray from what we have covered so far. There really are some excellent examples given there. So I hope, in spite of this limitation, that you have found this video useful. And that ends video 4, and we now await the final video, video 5, which will allow us to understand and practice actually carrying out a meta-analysis using RevMan. As usual, here are my references to accompany these slides. And as promised, the 2 videos that I mentioned at various points in the presentation. You will of course need to access the slides version to click on the links. And finally, my usual disclaimer regarding images borrowed from this presentation. So once again, thank you for your attention, and I'll see you in the next and final video. Cheerio.